Welcome back at the FinetLink channel. We are focused at the transport layer, reminding you that the objective of this material is to compare the operation of transport layer protocols in supporting end-to-end communication. And now we are at the part 2. At the first part, we explained the purpose of the transport layer in managing the transportation of data in end-to-end communication. We explained the characteristic of the TCP protocol and the UDP protocol, and we even explained how the TCP and UDP use port numbers. And now, in the second part of the transport layer, we will explain how TCP session establishment and transmission process facilitate reliable communication, and we will explain how the TCP protocol data units are transmitted and acknowledged to guarantee delivery. And lastly, but not least, we will compare the operation of transport layer protocols in supporting end-to-end communication. At the first part of the transport layer, we discussed about the port numbers. Understanding the role of port numbers will help you to grasp the details of the TCP communication process. Each application process running on a server is configured to use a port number. The port number is either automatically assigned or configured manually by a system administrator. An individual server cannot have two services assigned to the same port number with the same transport layer service. For example, a host running a web server application and a file transfer application cannot have both configured to use the same port, such as TCP port 80. An active server application assigned to a specific port is considered open, which means that the transport layer accepts and processes segments addressed to that port. Any incoming client request addressed to the correct socket is accepted and the data is passed to the server application. There can be many ports open simultaneously on a server, one for each active server application. Let's see the steps. First, we have the client sending the TCP request. And as you can see here, we have the client 1, which is requesting a web service, and client 2, which is requesting email service on the same server. Now we have the request destination port. At the request destination port, client 1 is requesting web service using well-known destination port 80 for HTTP protocol. And client 2 is requesting email service using well-known port 25, known for SMTP protocol, Simple Mail Transfer Protocol. And for the request source port, you can see that the client request dynamically generate a source port number, and in this case, client 1 is using source port as it is shown here for 9152, and the client 2 is using this source port 51152. And as the response to the destination port, you will see that when the server responds to the client request, it reverses the destination and source port of the initial request. You may see that the server response to the web request now has the destination port as it was the source port at the request source port, and the destination port for the email response will be this one. And the last one is the response source ports. And at the response source port, you will see that the source port in the server response is the original destination port in the initial request, as you can see here. And for the TCP connection establishment, you may know that in some cultures, when two persons meet, they often greet each other by shaking hands. Both parties understand the act of shaking hands as a signal for a friendly greeting. Connections on the network are similar too. In TCP connection, the host client establishes the connection with the server using the three-way handshake process. And you may ask how this process works. There are three steps for this three-way handshake process. The first step is the step for synchronization. With this, the initiating client requests a client-to-server communication session with the server, and it is shown here. So the client will send a synchronization with the server. And the first step is the acknowledgement and synchronization step. And with this one, the server acknowledges the client-to-server communication session and requests a server-to-client communication session too. And the last step of the three-way handshaking process, it is the acknowledgement. And with this one, it is the initiating client acknowledge the server-to-client communication session. And as you can see, there is a time between each step, and there is a sequence number for each of synchronization and acknowledge process. That was for the establishment of a session between the client and the server. And there is other option. There is the step of session termination. And to close a connection, you have to use the finish control flag that must be set in the segment header. To end each one-way TCP session, a two-way handshake consisting of a finish control segment and an acknowledgement segment that need to be used. Therefore, to terminate a single conversion supported by the TCP protocol, there will be 4 exchanges to end this session. Either the client or the server can initiate this termination process. In the example, the terms client and server are used as a reference for simplicity, but any two hosts that have an open session can initiate the termination process. And as I said, there are 4 steps. The first step is the finish control flag, the finish control segment, And it is when the client has no more data to send in the stream, so it sends a segment with the fin flag set, as it is shown here. The second step is the step of acknowledgement. In this case, the server sent an acknowledgement the receipt of the fin segment to terminate the session from client to server. And then we will have the third step. The third step is the fin segment, but in this time, the server will send a fin to the client to terminate the server to client session. So we'll send a fin segment now to the client. And the last step will be the acknowledgement step. And in this case, the client will respond an acknowledgement segment to the fin segment from the server. So, and after this step, the session has terminated. Let's analyze the TCP three-way handshake. Hosts maintain state, track each data segment with a session, and exchange information about what data is received using the information in the TCP header. The TCP protocol is a full duplex protocol where each connection represents two one-way communication sessions. To establish the connection, the host performs a three-way handshake. There are the function of the three-way handshake as to establish that the destination device is present on the network, to verify that the destination device has an active service and is accepting requests on the destination port for that initiation client intended to use, and to inform the destination device that the source client intends to establish a communication session on that port number. And as it is shown here in the figure, there are control bits in the TCP header that indicate the progress and status of the connection. After the communication is completed, the sessions are closed and the connection is terminated. The connection and session mechanism enable the TCP reliability function. The 6 bits in the control bit field on the TCP segment header are also known as flags. A flag is a bit that is set to either on or off. The 6 control bits flags are as is shown here. We have the urgent pointer field significant. We have the acknowledgement flag used in connection establishment and session termination. We have the push function. We have the reset the connection when an error or timeout occurs. We have the synchronized sequence number used in connection establishment, and we have even the fin segment with fin flag, where no more data from sender and used in session termination. There are reasons that the TCP is the better protocol for some application, because unlike UDP protocol, it resends raw packets and number packets to indicate their proper order before delivery. TCP can also help maintain the flow of packets so that devices do not become overloaded. There are times when the TCP segments do not arrive at their destination. Other times, the TCP segments might arrive out of order. For the original message to be understood by the recipient, all the data must be received and the data in these segments must be reassembled in the original order. Sequence numbers are assigned in the header of each packet to achieve this goal. The sequence number represents the first data byte of the TCP segment. During the session setup, an initial sequence number is set. This initial sequence number represents the starting value of the data bytes that are transmitted to the receiving application. As data is transmitted during the session, the sequence number is incremented by the number of bytes that have been transmitted. This data byte tracking enables each segment to be uniquely identified and acknowledged. Missing segments can then be identified. The initial sequence number does not begin at 1, but it is officially a random number. This is to prevent certain type of malicious attacks. For simplicity, we use an initial sequence number of 1 for the examples in the material that we are discussing. Segment sequence number indicate how to reassemble and reorder the received segment as it is shown here in the figure. The receiving TCP process places the data from a segment into a receiving buffer. Segments are then placed in the proper sequence order and passed to the application layer when reassembled. Any segments that arrive with sequence number that are out of order are held for later processing. Then, when the segments with the missing bytes arrive, these segments are processed in order. And as for the data loss and the retransmission, no matter how well designed a network is, data loss occasionally occurs. The TCP provides method of managing these segments losses. Among these is a mechanism to retransmit segments for acknowledged data. The sequence number and acknowledgement number are used together to confirm receipt of the bytes of data contained in the transmitted segment. The sequence number identifies the first byte of data in the segment being transmitted. The TCP uses the acknowledgement number sent back to the source to indicate the next byte that the receiver expects to receive. And this is called the expectational acknowledgement. We said that TCP could only acknowledge the next byte accepted. For example, here in the figure, we are using segment numbers for simplicity. Host A is segments 1 through 10 to the host B. If all the segments arrive except the segment 3 and 4, host B would reply with acknowledgement specifying that the next segment expected is segment 3. Host A has no idea if any other segments arrived or not. Host A would therefore resend segment 3 through 10. If all the recent segments arrive successfully, segment 5 through 10 would be duplicated. This can lead to delays, congestion, and inefficiencies. Host operating systems today typically employ an optional TCP feature called selective acknowledgement, negotiated during the three-way handshake. If both hosts support the selective acknowledgement, the receiver can explicitly acknowledge which segments were received, including any discontinuous segments. The sending host would therefore only need to retransmit the missing data. And this is shown here in the figure. For example, again using segment number for simplicity, host A is sending segment 1 through 10 to host B. If all the segments arrive except for the segment 3 and 4, host B can acknowledge that it has received segment 1 and 2 and selectively acknowledge segment 5 through 10, and then host A would only need to resend the segment 3 and 4. TCP uses timer to know how long to wait before resending a segment. Another feature of the TCP is providing mechanisms for flow control. Flow control is the amount of data that the destination can receive and process reliably. Flow control helps maintain the reliability of TCP transmission by adjusting the rate of data flow between source and destination for a given session. To accomplish this, the TCP header includes a 16-bit field called the window size. And here in the figure, it is shown an example of window size and acknowledgement. The window size determines the number of bytes that can be sent before expecting an acknowledgement. The acknowledgement number is the number of the next expected byte. The window size is the number of bytes that the destination device of TCP session can accept and process at one time. Here in this example, the PCB initial window size for the TCP session in 10,000 bytes. Starting with the first byte number 1, the last byte of the PCA can send without receiving an acknowledgement is byte 10,000. This is known as the send window of the PCA. The window size is included in every TCP segment, so the destination can modify the window size at any time depending on buffer availability. The initial window size is agreed upon when the TCP session is established during the three-way handshake. The source device must limit the number of bytes sent to the destination device based on the window size of the destination. Only after the source device receives an acknowledgement that the bytes have been received can it continue sending more data for the session. Typically, the destination will not wait for all the bytes for its window size to be received before replying with an acknowledgement. As the bytes are received and proceed, the destination will send acknowledgement to inform the source that it can continue to send additional bytes. For example, it is typical that PCB would not wait until all 10,000 bytes have been received before sending an acknowledgement. This means that the PCA can adjust its send window as it receives acknowledgement from the PCB. As it is shown here, when the PCA receives an acknowledgement with the acknowledgement number 2921, which is the next expected byte, the PCA send window will increment to 2920 bytes. This changes the send window from 10,000 bytes to 12,920. PCA can now continue to send up to another 10,000 bytes to PCB as long as it does not send more than its new send window at 12,920. A destination sending acknowledgements as it processes data byte received, and the continual adjustment of the source send window is known as sliding window. The send window of the PCA increments or slides over another 292 bytes from 10,000 bytes to 12,920 bytes. If the availability of the destination buffer space decreases, it may reduce its window size to inform the source to reduce the number of bytes it should send without receiving an acknowledgement. And here in this figure, there is the source that is transmitting 1,460 bytes of data within each TCP segment. This is typically the maximum segment size that the destination device can receive. The maximum segment size is part of the option field in the TCP header that specifies the largest amount of data in bytes that the device can receive in a single TCP segment. The maximum segment size does not include the TCP header. It is typically included during the three-way handshake. A common maximum segment size is 1460 bytes when using the IPv4. A host determines the value of its maximum segment size field by subtracting the IP and TCP headers from the Ethernet maximum transmission unit. And on an Ethernet interface, the default maximum transmission unit is 1500 bytes. Subtracting the IPv4 header of 20 bytes and the TCP header of 20 bytes, the default maximum segment size will be 1460 bytes, as it is shown here in this figure. There are times when congestion occurs on a network. It results in packet being discarded by the overload router. When packets containing TCP segments do not reach their destination, they are left unacknowledged. By determining the rate of which TCP segments are sent by not acknowledged, the source can assume a certain level of network congestion. Wherever there is congestion, retransmission of lost TCP segments from the source will occur. If the retransmission is not properly controlled, the additional retransmission of TCP segments can make the congestion even worse. Not only are new packets with TCP segments introduced in the network, but the feedback effect of the retransmitted TCP segments that were lost will also add to the congestion. To avoid and control the congestion, the TCP employs several congestion handling mechanisms as timers and algorithms. If the source determines that the TCP segments are either not being acknowledged or not acknowledged in a timely manner, then it can reduce the number of bytes it sends before receiving an acknowledgement. As it is illustrated here in the figure, the PCA senses that there is congestion and therefore reduces the number of bytes it sends before receiving an acknowledgement from the PCB. You may see that it is the source that is reducing the number of unacknowledged bytes it sends, that, and not the window side determined by the destination. And as for the UDP protocol, as we explained before, is perfect for communication that need to be fast, like voice over IP. We will explain in details why UDP protocol is more perfect for some types of transmission. As it is shown here in the figure, UDP does not establish a connection, provides low overhead data transport because it has a small datagram header, and no network traffic management. Like segments with the TCP, when UDP datagrams are sent to a destination, they often take different paths and arrive in the wrong order. UDP does not track sequence number the way TCP does. UDP has no way to reorder the datagram into their transmission order, as it is shown here in the figure. Therefore, the UDP simply reassembles the data in the order that it was received and forwards it to the application. If the data sequence is important to the application must identify the proper sequence and determine how the data should be processed. Like TCP-based application, UDP-based server application are assigned well-known or registered port number as it is shown here in the figure. When this application or process are running on a server, they accept the data matched with the assigned port number. When UDP receives a datagram for one of these ports, it forwards the application data to the appropriate application based on its port number. And as for the UDP client process, the client server at the TCP communication is initiated by a client application that requests data from a service process. But at the UDP client process, dynamically select a port number from the range of the port number and uses this as a source port for the conversation. The destination port is usually the well-known or registered port number assigned to the server process, same as the TCP. After a client has selected the source and destination port, the same pair of ports are used in header of all datagrams in the transaction. For the data returning to the client from the server, the source and destination port in the datagram header are reversed. And let's see each of those processes. First, we have the client sending UDP request. And as you can see here, the client 1 is sending a DNS request, while the client 2 is requesting radius authentication service from the same server. And we will have the UDP request destination port. The client 1 is sending a DNS request using the well-known port 53, while client 2 is requesting radius authentication service using the registered destination port as 1812. And then we will have the UDP request source port. In this case, the request of the client dynamically generates source port number, and the client 1 is using this source port number, and the client 2 is using this one that are highlighted in orange. Then we will have the UDP response destination. And as you can see, when the server responds to the client request, it reverses the destination and source port of the initial request. And in the server response for the DNS request is now the destination port as it is highlighted here. And the port that is highlighted here will be the radius authentication response as a destination port. And lastly will be the UDP response source port. And here you will see that the source port in the server response are the original destination port in initial request. And with this information, we are ending up the second part of the transport layer. Thank you for being with us, and do not forget to subscribe at our channel and hit the notification button for the new videos that will be uploaded.